Greetings, I'm Nur Rifqah Sait, and today I'm going to present regarding my final year project, which is development of PVDF membrane via vapor-induced phase separation for oil-water emulsion separation. Before I start my presentation, allow me to introduce myself. I'm Nur Rifqah Sait with ID number 23617. So, this is my agenda layout for my presentation today, which I will be explaining in further details. Firstly, I'll talk about introduction, starting by background project. In this modern era, our Mother Earth currently is facing with endless challenges of environmental and ecological pollutions due to human actions and industrial activities. One of the major threats is due to the rapid industrial development, such as in oil and gas, food industry, which has led to the large production of oily wastewater. Oily wastewater has also been recognized as the most dangerous form of environmental pollution. Hence, this oily wastewater needs to be treated as to achieve purified water, which can either be reused or to discharge safely to the environment. So, there are various technologies in purifying the oily wastewater, which include conventional physical and chemical methods such as sand filter, adsorption oxidation, electrochemical process, and many others. Unfortunately, these conventional methods suffer few limitations, such as expensive, require large space for installation. Hence, in this 21st century, membrane technology has been introduced and served as an emerging technology, especially in treating oily wastewater. Moving on to the literature review, membrane separation technology is one of the most effective separation technologies in treating oily wastewater, which is due to its small footprint, high efficiency of oil removal, consistent quality of effluent, low investment and operation cost, and operational simplicity. Indeed, membrane separation process is economically effective and known as greener approach. However, there are few types of pressure-driven membrane processes, which include microfiltration, ultrafiltration, nanofiltration, and reverse osmosis. Hence, this research study will be utilizing the pressure-driven microfiltration membrane throughout conducting the experiments. This is the simple illustration on how membrane works. A membrane undergoes separation process, which can be defined as a selective barrier between two phases. The principle of how a membrane works is quite simple, where a feed passes through the membrane, which is influenced by a driving force, thus splitting the feed into two sections, which include a retained teeth that is retained or rejected by membrane, and a permeate that passes through the membrane as the required product. There are numerous types of polymers that are regularly used upon membrane fabrication, such as polyvinylidene difluoride and polysulfate, and many others. Each type of polymer has its own characteristics that fit the researcher's demand. However, polymers such as PVDF has been used for preparing microfiltration and ultrafiltration membranes for treating various types of wastewater, including emulsified oil water mixtures. PVDF also attracted most of the researchers' attention, probably due to its outstanding antioxidation activity, high thermal stability, good organic selectivity, and excellent chemical and mechanical resistance. Unfortunately, PVDF membrane possesses some disadvantages, which include tendency to fall more quickly, thus resulting in flux decline and rejection deterioration. For problem statement, there are a few current challenges that membrane filtration is facing by. Firstly, include membrane fouling. Oily wastewater contains a lot of impurities and highly toxic substances, and some of the molecules are sticky in nature, which resulting in membrane fouling. Membrane fouling eventually leads to severe decline in flux, as well as impedes long-term operation of a membrane process. This figure portrays the oil fouling in oily wastewater filtration. Firstly, oil droplets partially blocking the membrane pores. Then there is a cake layer formation on the membrane. Soon there will be contiguous oil film on the membrane. And lastly, the oil droplets clog within the membrane pores, which resulting in membrane fouling. Simply blending the hydrophilic additives into casting solution by employing the non-solvent induced phase separation for membrane fabrication results in leaching out of the additive during membrane fabrication and relatively small pore size. Therefore, this research explores fabrication of hydrophilic PVDF-based membrane using PVP as the hydrophilic additive by using the WIPS technique. WIPS method is expected to provide additional degree of freedom in turning the surface property of the resulting membrane. Due to the fouling, PVDF needs to modify in order to increase the flux. Indeed, it is generally agreed for the application of purification of oily wastewater, polymer-dominated membranes must be more hydrophilic in order to prevent the addition of oil droplets on the membrane surfaces. Hydrophilic additive such as PVP, which is used in my experiment, is commonly used to increase the hydrophilicity and elasticity of asymmetric membrane during membrane fabrication. So, this illustration illustrates the mechanism occurred during the separation of stable oil-water emulsion using unmodified and modified membrane. The main purpose of the surface coating is to form a layer of materials with anti-fouling properties. Hence, the tendency of oil droplets to assemble on the membrane surface could be reduced. All droplets which pass through the membrane pores would most likely block the water molecules to pass through the membrane. Then the water permeability would significantly decrease after a long period of time. Hence, it is suggested that the best materials for surface coating should possess hydrophilic properties such as PVP. This is the summarized table of my literature review. In general, from this table, it can be observed that all of these researchers are attempting to improve the performance of PVDF membrane by adding some additives, for instance, polydopamine, titanium oxide, zwitterionic polyelectrolyte, and different approach will result in different value of permeability, rejection, oil contact angle, and water contact angle. Of 4 methods which include non-solvent induced phase separation (NIPS), thermally induced phase separation (TIPS), evaporation induced phase separation (EIPS), and vapor induced phase separation (VIPS), or the combination of these methods. However, in this research study, I will be focusing more on the fabrication of membranes via VIPS. VIPS process happens when there is penetration of non-solvent from a vapor phase to polymer solution, thus inducing phase inversion. This method also enables better controlling of the desired membrane morphology during the separation of phase, which can be attained by proper monitoring and regulating of the phase inversion process during fabrication step. VIPS also allows hydrophilic polymers such as PVP as polymer solution additives to boost the hydrophilicity of the resulting membrane surface. This study focuses on development of PVDF membranes via the VIPS method to enhance membrane fouling resistance. The objectives include to fabricate and characterize PVDF-based membranes with PVP as additive via the VIPS, to evaluate the performance of the developed membranes in terms of hydraulic or rejection and anti-fouling properties for filtration of oil-water emulsion. For scope of study, this research study is directed towards the fabrication of PVDF membranes with hydrophilic pores, which are carried out by using VIPS technique. This includes the development of 5 different types of membrane by utilizing 4 types of chemicals with the time gaps of 0 minute, 5 minutes, 15 minutes, and 30 minutes. A plain PVDF membrane is also being fabricated as reference to other membranes. The research is limited to be conducted at a pressure difference of 0.2 bar by using cross-flow microfiltration system with width of 1 gram per liter of oil-water emulsion. Next, moving on to the methodology. So, this is my project workflow, started with research methodology and ended by compilation of data and data analysis. Next, membrane fabrication. All membranes will be fabricated using PVDF as polymer, whereas dimethyl acetamide DMAC as the solvent. Furthermore, non-woven support will be utilized in providing mechanical strength for the developed membranes. This figure portrays the schematic diagram of the procedures of fabrication of membranes as applied in this research study. And this table shows the type of membranes used in this research study. For membrane characterization, this table shows the membrane characterization utilized in this experiment. Those properties of the membranes are important to evaluate the hydraulic performance and to assess if the proposed membrane fabrication method was effective in enhancing the properties and performance of resulting membranes. Next, membrane filtration. These figures show the real-life setup and illustration setup of the experiment. The hydraulic performance of the developed membranes will be evaluated using cross-flow microfiltration. And for this study, oil-water emulsion will be used for all filtration tests as fit. And these are the experimental calculations used for filtration and anti-fouling analysis, which include flux, permeability or rejection, total fouling, reversible and irreversible fouling. And lastly, this is the Gantt chart for both of my FYP1 and FYP2. Moving on to the next segment, which is results. Firstly, I will discuss regarding membrane characterization for membrane morphology. So, this figure shows the morphological images of the plain PVDF membrane, MREF, and the modified PVDF membranes of M0, M5, M15, and M30. The results demonstrate a clear relationship between the exposure time with the morphology of resulting PVDF membranes. The pristine PVDF, MREF, and M0 membranes both have typical asymmetric structures with dense top layers and have large microvoids with finger-like substructure near the top surface. So the microvoids formed in M0 are smaller as compared to MREF. Generally, the formation of morphology transforms from finger-like microvoids to sponge-like pores, which is commonly found for Webb's base membrane. Unfortunately, based on SEM images for both M15 and M30 membranes, both of the membranes are not well intact in terms of morphology. Meanwhile, in terms of mechanical properties, M30 is the weakest as the polymer clusters loosely attach each other. Next, I will explain regarding membrane pore size and distribution. Addition of PVP and lithium chloride into the DOP solution resulted in slight increase in the membrane main pore size from 0.210, which is the MREF, to 1.549, which is the M0. Extending the exposure time before the process of emission would remarkably increase membrane pore size to this value, which is for the M5, M15, M30 respectively. Obvious difference in pore size can be explained due to the addition of PVP and lithium chloride as additive, which giving the impact of thermodynamic rather than the kinetic. The PVP is able to increase the viscosity, thus impeding the fast separation kinetics, but significantly enhancing the thermodynamics for the fast separation due to its good hydrophilicity. Hence, in Webb's process, nucleation plays a crucial role in the polymer lean phase as well as contributes to the formation of highly porous membrane. Therefore, it is recognized that through the polymer chains, an increase in solution viscosity eventually limits water passage, forming of spongy matrix and more porous top surface, thus leading to the formation of larger mean pore size. Moving on to the surface contact angle, Figure 3.3 portrays the dynamic water contact angle of the resulting membrane samples. According to Hebar, surface contact angle is used to evaluate the surface hydrophilicity of the membrane. The contact angle of MREF is much higher than M0, implying that MREF possesses greater hydrophobic properties. M30 shows the highest contact angle, most likely because of lattice effect, where it is known for having the properties of highly water repellent or superhydrophobic surface, which attributing to the double roughness structure that consists of the mixture of macrostructure and microstructure. To further justify this phenomenon, it is believed that lattice effect occurs in M30 not because of the PVP washout, but the extended exposure time indeed causes the membrane surface to be rougher, explaining the higher value of contact angle. M15 initially portrays the same phenomenon as M30, but then M15 eventually is showing the property of hydrophilicity as the contact angle decreases over the observed time. M0 and M5 show flat surface morphology and has low pore size, which indicating their ability to retain the PVP to impose hydrophilicity, which indeed portray the best result for this analysis. In terms of FTIR, the FTIR spectra in figure 3.4 implies on how Webb's can positively enhance the membrane surface hydrophilicity. Every resulting membrane portrays peaks at 1402, which indicates there is presence of CH bending vibration, and 1180, which indicates there is presence of CF stretching vibrations, respectively from the PVDF chain. Moreover, a new peak can be observed at 1660 for all the modified PVDF membranes attributed to the presence of residual PVP. Moreover, characteristic peaks of C double bond O bond in PVP is observed at 1670, which indicating the presence of carbonyl group in the PVP according to Han. The most intense peak is shown for M0, followed by M5, M15, and M30, suggesting the higher exposure time promotes additive leaching due to larger pore size of the membranes prepared under longer exposure times. For EDX mapping, the increase of oxygen element confirms the presence of PVP in the PVDF membrane matrix. The presence of N element also indicates the presence of PVP in the membrane matrix. Moreover, the amount of distribution of F element significantly reduced, whereas the distribution of N and O elements show increment trend. From figure 3.5, the presence of an element present in PVP is because PVP belongs to amide carbonyl group. And next, for XPS, XPS is analyzed to further confirm the effect of extension time in enhancing of the residual PVP in the PVDF matrix. From figure 3.6, M0 has a higher oxygen peak as compared to M15, which suggests that M0 retains more PVP in the membrane matrix, supporting the finding of FTIR analysis. The higher retention of PVP can be explained by the smaller mean flow pore size of the membrane. The higher retention of PVP in M0 also leading to lower contact angle, hence more hydrophilic property. Furthermore, in terms of clean water permeability, the findings prove that the morphology as well as the pore size of the membrane influence the permeability. The MREF has the lowest value of CWP due to its smallest mean flow pore size. The small mean pore size restricts the transport of water droplets across the membrane film. M15 poses the highest permeability of 1527, followed by M0 of 1233 and M5 of 1131. M15 poses the highest permeability due to its largest pore size and good hydrophilicity. Even though the mean flow pore size of M5 is slightly larger than M0, the latter poses higher hydrophilicity of M0, indicating why M0 has higher permeability than M5. For the permeance analysis, the first part of the filtration was performed for 90 minutes by using clean water as the feed for compaction. Subsequently, the second part was conducted by using oil water emulsion as the feed for 30 minutes, followed by flushing with clean water for 5 minutes in order to complete one filtration cycle. The oil water emulsion filtration was conducted in 5 cycles. The permeabilities of clean water and oil water emulsion in every part were recorded to evaluate the trend. The depreciation of the permeability over time indicates the occurrence of membrane falling. The flux decline can only be delayed with appropriate control and cannot be completely avoided. M15 portrays the highest permeability in the first filtration cycle, followed by M0, M5 and MREF due to its large membrane pore size. After 180 minutes, M5 shows the highest permeability towards the end of the filtration, which demonstrates the advantage of its high hydrophilicity, which allow it to maintain high permeability by simply apply water flushing as a means for membrane falling control. In terms of rejection performance, only 3 membranes achieve oil rejection of above 80%. MREF has the lowest oil rejection, whereas M5 poses the highest oil rejection. All VIPS membranes have better oil rejection than MREF due to the presence of PVP in enhancing the hydrophilicity. So, the residual PVP enhances the hydrophilicity that promotes the penetration of water through the membrane, whereas repels the oil droplets. Thus, VIPS membrane has high membrane flux with low falling due to the presence of hydroxyl and ketone groups in PVP and their higher pore size. For the anti-falling property, this anti-falling property was assessed based on their reversibility, in which reversible falling can be eliminated by physical cleaning such as water flush, whereas irreversible falling needs chemical cleaning. Since MREF has the lowest permeability, it can be observed that it has the lowest falling rate. The permeability and contact angle affect the degree of physically irreversible falling, where this irreversible falling might correspond to M0 properties of relatively low surface contact angle, which is more hydrophilic and has greater clean water permeability, thus explaining why M0 is greater than M15 in terms of reversible falling. Overall, it shows that M5 membrane has the lowest tendency to fall due to its superior hydrophilicity. Lastly but not least, for the conclusion, this project has demonstrated that performance of PVDF-based membrane can be enhanced by applying VIPS fabrication method and addition of PVP and lithium chloride additives. This prolonged exposure time, which is from 0 to 30 minutes, changes the membrane morphology and structure from macrovoids with finger-like substructure to cellular structure, which also have bigger pore size. The results also validate the smaller the mean flow pore size, the higher the retention retention of PVP, thus leading to enhanced surface hydrophobicity, which is demonstrated from the FTIR spectra and EDX analysis. The overall results portray that M5 membrane results in the best hydraulic performance with improved clean water permeability by factor of 6 from the MREF and has ore rejection of 91% and also the lowest membrane falling properties. Moving on to the recommendations, there are 2 recommendations which include repeat the experiment and explore effect of VIPs by using different additives. And lastly, this is my references. Thank you, that's all from me.